Hi all, my name is Alex Avrilla. I am co-director at Carper AI, and today I will be talking about trlX, a framework for open source RLHF. So what is RLHF? RLHF is an acronym standing for Reinforcement Learning from Human Feedback, and you can think of it as a technique for fine-tuning language models to incorporate human preferences. And it can be roughly broken down into 3 stages. Number 1, first you collect pairwise comparisons among model responses to a given task. So for example, let's say I want to write happy stories. Look at the right-hand side. And the model generates 2 potential responses, one about a happy goose and one about a sad goose. Since I want to write stories which are happy, I'm going to select the response which is about a happy goose as more preferable to the response which is about a sad goose. These pairwise comparisons can then be used to train a reward model, which you can think of as an adapted language model which assigns a higher score or reward to the response which is preferred by the user. You can think of this reward model as an offline proxy for the human preferences which were captured in stage 1. Then, once this reward model has been learned, we optimize against it using a reinforcement learning algorithm, most commonly proximal policy optimization or PPO. And this results in a downstream student model which is able to write happy stories, or more generally, it's aligned to the preferences which were collected in stage 1 and distilled into a reward model in stage 2. And this makes up the RLHF pipeline. So some examples of popular RLHF models in the wild. ChatGPT, I think we're all familiar with. Most people have heard it by now. And this is an example of what we believe to be an RLHF model. It has been trained using reinforcement learning and optimized against a reward model which incorporates human preferences. However, there are other examples of RLHF models in the wild as well. So Anthropic AI, a competitor to ChatGPT, has their own model called Claude, which is trained in a similar way. And then the research group DeepMind also has their own version of this called Sparrow, which optimizes against a reward model specifically for web-based retrieval. However, one important caveat here is that these are all examples of closed source RLHF models. We don't have access to the underlying model weights, and we don't have access to the training data which was used to produce these models, or the training framework that was used to produce these models for that matter. And as a result, it's very hard to reproduce them or even go about studying them in any relatively rigorous way. In order to do this, we need open source RLHF models. But the problem here is that really currently there are no good large-scale open source RLHF models, yet at least. So at Carper AI, I, along with many others, are working to produce one of the first open source RLHF models. We plan to open source the model itself, as well as the training framework and the data that was used to train the model. And we anticipate this to be hugely impactful to a bunch of people, developers, researchers, even everyday folk who are interested in trying out some of these models. Probably researchers and developers for the most part, though. So why does open source RLHF matter? I mean, I kind of already touched on some of these points, but I think there are many people who feel that equal access for all to this kind of potentially world-changing technology is crucial. Carper AI is fortunate enough to be supported by Stability AI, who provides compute for us to train these RLHF models. And democratization of AI is central to Stability's mission. Giving people access to this kind of technology is crucial, I believe, and should not be left in the hands of the few. But perhaps most importantly, in my belief, is closed source RLHF makes good science fundamentally impossible. If researchers don't have access to the underlying model weights or to the underlying data, then we really have no idea how these models were really trained, and so it is hard for us to draw meaningful comparisons or study these models in any rigorous way. And due to the huge impact these models have been having in media in general, it's very important to be able to study them and understand them in a deeper way. So blockers to open source RLHF. What makes this problem difficult? So first, number 1, high-quality supervised fine-tuning data is generally difficult to find. There's kind of a step 0, which I didn't mention beforehand, before you collect preferences among various model outputs, which is you collect a bunch of high-quality responses, kind of telling your model what you want it to roughly do, and then you fine-tune it on these responses, and this kind of gets the model more in distribution. If you are from the RL domain and are familiar with the concept of behavior cloning, you can think of it as analogous to that. Number 2, once you have a supervised fine-tuned model, you still need access to high-quality preference data, which is, you present various responses to users and then have the users rank or choose which responses are most preferable. This is also relatively expensive to collect, and there are not that many examples out there in the wild. Number 3, and perhaps most underrated, you need a scalable training framework for language model fine-tuning via reinforcement learning. The dominant language model training paradigm over the last couple of years has been a supervised objective, such as semi-supervised objective, such as next token prediction, where you don't have to query an outside reward model or something like that. And so for particularly training models at scale, this makes adapting these scaling frameworks difficult to the RL domain, since you have many more moving parts with reinforcement learning. You need to host the reward model, you need to host the student model, and for online RL, you need to host other things as well. And this makes the compute and memory requirements that much more difficult to satisfy, which were already difficult for 70 billion parameter models. So where does trlX come in? So trlX addresses number 3, a scalable RL training framework. This was a training framework originally developed by myself and a couple others at Carper.ai. And as of right now, it is the leader in open source RLHF training at scale. It's an actively developed library which gets regular updates every week, and we hope for this repo to continue to be pushing forward open source RLHF training at scale, and we're excited to see where it goes. So what are some of the capabilities that trlX supports? When we were designing the library, we were cognizant of the fact that we would have users with a wide range of various user profiles using it. And so we tried to build in various training frameworks which accommodate each of these users separately. These are roughly divided into 3 cases. So first of all, you have your independent researchers with access to maybe a single GPU. And these can train up to about a billion parameter model using native PyTorch. But this is still pretty decent. You can get pretty good RLHF results with a 1 billion parameter model. If you have some more resources, so maybe multiple GPUs on a single node, you can consider training using Hugging Face Accelerate integration plus deep speed, which allows you to train about up to 20 billion parameter models. And this is quite good. And if you are a particularly well-endowed user with multiple nodes of 8100s or something, then we have tested our integration with the NVIDIA NeMo training framework, fine-tuning models up to 70 billion parameters. And this is competitive with the size of models you see in many of these Anthropic's papers, for example. And we're excited to see where this takes us. So what are some features that trlX supports? We have a good number. So first of all, we're compatible with most encoder-decoder, such as T5 models, and decoder-only models, such as GPT-NeoX, which are supported on Hugging Face. This makes loading and saving models relatively easy and efficient. Also, like I said, we were cognizant of the fact that we want this library to be accessible to many different users and use cases, particularly independent researchers who have limited resources. So we've incorporated several memory saving / compute efficient features, including low rank adaptation or LoRa, 8-bit atom, layer freezing, and Hydra. And we'll go into these in more detail later. But in general, you can think of these as reducing the memory requirements to do RLHF. We've also incorporated various online and offline reinforcement learning algorithms, which have their various trade-offs and benefits, which I'll talk about later. And perhaps most importantly, we have support for multi-GPU hyperparameter sweeps, which are very important for reinforcement learning, which it's integrated with weights and biases, which we use for experiment tracking. And this is very useful. We use it in the future every day. Additionally, we have 10 plus built-in examples of varying complexity, which users can run and get started with and start building their own. So let's dive in a little more and look at the anatomy of language model fine-tuning via online reinforcement learning at scale. So this is kind of a complex process, and at training time, you have many different models which you need to hold in memory. So first, you need the model that you're fine-tuning, the student model, which you can think of as your policy. And you also need the value head of this policy, which is used for proximal policy optimization, or PPO. And if you're not familiar, you can think of this value head as kind of trying to learn and approximate the reward that a given response will generate. Additionally, we have this reference model, frozen reference model, which is used to kind of produce some kind of KL control penalty, enforcing the student model. It doesn't kind of overfit to the reward too hard. And additionally, we need to hold in memory the reward models themselves, which can be quite large. And so altogether, if you were to treat each of these models as separate, a value network separate from a student network, separate from a reference network, separate from a reward network, that's a high bar. It requires a lot of compute and a lot of memory. However, trlX leverages a recent architecture introduced by Sparrow, DeepMind's paper Sparrow, called the Hydra architecture, which fuses together all these models into kind of one shared trunk with shared layers. And this is made feasible by the fact that most of these models have their layers frozen already. For example, the reference model is frozen, it's not being optimized. The reward models are frozen, they're just being inferenced. Really, it's just the student that we're training. And in many cases, it doesn't even make sense to train the majority of the student anyway. We want to freeze most of the layers to provide more stability. And we find that in some cases, this can save up to 75% of the memory required otherwise if we were to treat these all as separate networks. And this really makes it more accessible to all our different user groups, and we definitely recommend this feature. To demo the trlX library, let's do a warm-up. Let's say we're fine-tuning GPT-J, which is a 6 billion parameter model, to produce positive movie reviews. How would we do this? Well, we're going to use a reward model, which is distilled by IMDb, 55 million parameters, and it's been trained to classify movie reviews into positive and negative sentiment. And then we're going to use proximal policy optimization, or PPO, which is an online RL algorithm. The environment we'll be training in is using 40 gigabyte 8 A100s, and we'll be using DeepSpeed 02 as our trainer. And what are the results? So we see that things look pretty good. After a couple hundred steps, the reward that we get is quite high. Note the reward from DistillBert is between 0 and 1. It is effectively just calculating the probability that the resulted text is positive or negative. And yeah, the reward looks stable, things increase quickly, life is good. Now, drawing your attention to the graphs on the right-hand side, we have the top, which is explore time, and we have the bottom, which is backward time. And these kind of represent the time that the algorithm takes to do the two main components of the, I guess, reinforcement learning training loop with language model. Explore time represents the time it takes to generate rollouts and allow the model to generate new experiences, which are then stored in a replay buffer and used at train time. And then we see that this takes a while. I mean, a 6 billion parameter model is relatively expensive to infer, right? And we're trying to generate a story, which means it needs to be inferred, up to 40 times for each movie review. And this is expensive, it can take up to 3 seconds. And it's definitely the bottleneck of the computation. So reducing or eliminating entirely the rollout time is very ideal if we're trying to speed up training. Compare this to the amount of time it takes to do a backward pass on the model. And we see that, the backward time is a fraction of the time that rollout takes. So optimizing rollout is quite ideal. This slide is just to allow you to qualitatively evaluate the results of the optimization. The reward that you see on the right, like I said, is between 0 and 1, so a reward of 0.99 is basically as good as you can get. So pause here if you want to examine some of the qualitative results. So some takeaways from fine-tuning for sentiment. Pros. Relatively sample efficient. Like I said, you see that reward goes up pretty fast, right? Also, the reward is stable, which means that, reward is going up reliably. You don't see it fluctuating up and down stochastically. But cons. So online RL is pretty difficult to scale. You have to have several different copies of the model in memory at times. You need the value network, you need the policy, you need the reference model, and you need the reward models. And this is somewhat alleviated by the Hydra architecture, like I said, but still expensive. And then it's also somewhat prone to reward overfitting. And what I mean when I say this is, if you look at a couple of these samples here, you notice that just even of these 6 samples, the first generated token is about music, right? And this is kind of representative of an underlying phenomena you will see, which is the more you optimize against a reward, the more overfit you will become, and the less diversity of generated text you will see. And this is particularly bad with online algorithms versus offline algorithms. I would say it's a significant drawback. So, you want your reward to be pretty high so that you've done a good job optimizing. But you don't want your reward to be so high that it's obvious that you've overfit, and the resulting text is obviously wrong, but rated highly by the reward model, because the reward model is an imperfect representation of the human preferences it's trying to capture. So now, with that in mind, let's take a look at a more advanced case study, where we are training a 20 billion parameter model, GPT-NeoX, to generate summarizations of some Reddit stories. The reward model will be fine-tuned GPT-J, and we'll be using instead an offline algorithm here, which is implicit language queue learning. The environment we're in will be 40 gigabyte 8 A100s again, and the trainer we'll be using is DeepSpeed 02. Well, we see that the reward that we compute goes up pretty quickly. Looks like training is still stable, and we converge to a reward of about 2.5. And perhaps more notably, the training time which it takes to do a full forward-backward pass is only 3 seconds, which is, when you compare it to the amount of time it takes to generate rollouts in the online case, very competitive, especially when you consider the fact that the model we're fine-tuning here is 3 times the size of the student model in the sentiments case, and with a much larger context. And I just want to point out here that because we're doing offline RL, no rollouts are required, which is a component of the fine-tuning procedure, it's the bottleneck. It takes the most amount of time. And so because we've managed to eliminate that bottleneck, we find that offline reinforcement learning is much more efficient in terms of compute and wall-clock time. And I let you survey some qualitative results here. I'm not going to read you the story, but you can pause if you want to. And if you look at the summary, I'd say the summary is pretty decent. In order to properly evaluate these models, you would need to deploy them to users, have them rank their responses, and then compute win rates. But just looking at the reward here and doing a qualitative analysis is pretty good as well. And it lets you get a feel for how well these models are performing. So some takeaways for the second fine-tuning for summarization example. Pros. Relative to online RL, offline RL is compute efficient. Training time is much faster. It's easier to scale, meaning that the offline RL objective and training framework is much more similar to the kind of training that you see doing supervised fine-tuning, and so it's much easier to implement code-wise and architecture-wise than online. And it's also relatively robust to overfitting because we're doing it offline and we're not actively interacting with the reward model. However, cons are, if you're really trying to get a high reward and optimize your reward model as far as you can, online is going to do better than offline. And to decide between the two, you're just going to have to judge yourself and mix and match, perhaps. So kind of summarizing the takeaways here, we have this nice little table. On the left, PPO and LQL, and then on the top, we have ease to scale. One is better, one is not. Compute efficiency, offline is a little better, online is a little worse. Robustness to overfitting, we have observed online is a little worse, offline is a little better. And then really maximizing the reward. So in this case, online does pretty well, offline not quite as good. I do want to say here, though, that these are just the results of our study, and this is very much so an active area of research. So, these could be domain-specific phenomena which we are discovering, and so I would definitely recommend doing your own experiments as well to get a sense of what works well. So, in conclusion, trlX provides a scalable, flexible framework for training models up to 70 billion parameters with reinforcement learning, an online and an offline trainer for various use cases in different scenarios, 10 plus examples of varying complexity ranging from beginner to research level, which users can get started with and start plugging in. And finally, integration with weights and biases for experiment tracking and hyperparameter sweeps, which I again want to emphasize are crucial for reinforcement learning. Hyperparameters are quite finicky, and to get really the maximum performance, you need to do a thorough search space of your hyperparameters. So this concludes the presentation. I attached some resources here at the end. Otherwise, thank you for listening.